So I'm opening secret.exe. And it's going to be a portable executable for a 386. That's an old type of processor. Linked with debug information, we'll load that. And that's just what variables are called, because the variable names get obscured by the assembler, right? Machine code doesn't care what we call the variable, it's just a number. So we're looking at this little red arrow right here. That red arrow is analyzing the code, and it's trying to determine what code does what. So we can see, right along this big long bar at the top, the different parts of the program. The blue is code. The green is data, and the purple and gray and whatnot is other types of data. Right? So for instance, here we can see a lot of the different names of Windows functions that we have to call. We don't concern ourselves with that, right? This data is encrypted data that we'll be cracking out of it in a minute. This we don't have to concern ourselves because we're going to change the assembly code. Now this is the cool part. I'm going to try to make this a little bit bigger. Okay. So what we see right here is the assembly code, right? This looks like assembly. And we have our overview of it right here. So we have a block of assembly that runs, and you'll notice that it has a jump not 0, right? So what we do is we compare. We're going to compare this pointer, EAX, plus this value. What that does is it gets the memory at that address to the value 4550 hexadecimal. It's going to set a flag. That's a 1-bit value. It's stored with an SR latch, right? Remember what we did on day 1. And that's in a special register called the flags register. If that is 0, which means if it's not 0, if it's not equal, then we're going to jump. We're going to jump to here, and that's going to follow this pathway down. Otherwise, we're just going to move to the next command, which is right here. So IDA is a really good disassembler in that it chunks our code up into blocks and shows us very visually with arrows how each block interacts and how one thing flows into another, right? So we can go along here, we can see that that one, it follows that red arrow down the side there and ends up in this block if it jumps, right? And that's that label that it was jumping to. Everyone following so far, right? The part we're interested in is right here. So here we have what's essentially setting encrypted data. Our secret.exe that I gave you is, I was actually sneaky with it. The source code I showed you before is not the real source code. I added a little bit that's going to print a special secret, and it's only going to print that if we can successfully reverse engineer it here in our IDA disassembler. To do that, we'll notice that at the beginning it prints the real secret is. And we see that right there at the beginning of that block, right? The real secret is. So we want to make this program get to that block. How do we do that? Well, I'm going to tell you that it starts off in this. I know because I wrote the program and because I've studied the disassembly fairly extensively before. It gets to this block. From there, it's got to get to this block. And then from there, it can get to, so this is the block where we enter the password, right? To explain what this assembly code does, we have this operator that's going to read in from Windows, right, the standard in operator. It's going to say, please enter the password or 0 to give up. It's going to call that. It's going to print it to the screen, right? It's then going to ask us for input, and it's going to call another Windows function that will get that. Have a good day. Once it's done there, we now have read in that password. Right, so we've read in the password. That's what happens in that block. What we do in the next block is we're going to compare the password. So we're actually going to do that twice. Right, the first time we're going to compare to see if it's the correct password. If it is the correct password, then we'll go on to where we could potentially go to the real secret or the fake secret, right? And the second block here, it's now going to compare to see if it's the real or if, not that if it's the real password, but it's always going to go to the fake password, or sorry, the fake secret. We're going to actually change the assembly to make it go to the real one, right? So we want to go from this, that it always runs up top, to this block here, which it should always get to, right? This block only exists as a separate block because something else can come into it. That's that loop. When we enter 0 to retry, it's going to come back into this block to re-ask us the password. Judith? Okay, so you see the text in these blocks, right? That text is assembly code. In reality, the assembly file, if we disassembled it, is just a big long file, right? We can break it up into these blocks, and these blocks are a little chunk of assembly here, a little chunk here, and then we can arrange them with the arrows pointing between them to show the program flow. Yeah, so a loop in assembly looks like code, 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 jump, label, and then label. Code, 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 jump, label. What it looks like in here is block, arrow from bottom to top, right? So that's what these blocks mean. And for an if, right, we could say jump if equal, and if that's the case, we'll jump to one of two other blocks that can then have arrows pointing elsewhere. Other questions on that? So that's what the blocks mean. So it's going to get to this where it asks for the password. We now want it to get to this block, and then to the one where it says the real secret is. To do that, we're going to enter a breakpoint. So I'm going to right-click here and add breakpoint. I'm also going to add a breakpoint right here, right? So we compare, and then we go to this jump, and we're going to stop. And then IDA's going to say, this program is run to this point. Now you can do what you will with the memory and the registers, and then I'll keep going. So where compare sets that flag bit, I'm now going to change the flag bit to what compare said it wasn't. So that's going to alter the program flow mid-execution and make it jump somewhere that compare said it shouldn't jump to. I'm going to do that twice. Once to make sure it gets to this second block here, once to make sure it gets to the real secret. So let's try it. So I'm going to go debugger, start process. I do want to, it just gives me a warning. And now we get to the first breakpoint. I look at that, this is a move, right? This one we're not interested in, so we're going to continue. I don't want to pass the fact that we stopped the application. I don't want to tell the program that we're stopping it, right? So I click no. And now we see the program, it's asking us for the password. I'm going to enter whatever I want. And now we get to this first jump not 0. And let's look at our flags register, the 0 flag, right? We can see that this is 1. So 1 means that it is not 0, that means it's going to jump. We don't want it to jump. So I'm going to enter 0, and then 0, hexadecimal 0. That flag now says we're not going to jump. I'm going to move on. It's now in that second block, and we're now at that second breakpoint. Right? We're at that second breakpoint, and this time we do want to jump. So it's a jump not 0. So we want to make it not 0. So I'm going to change the 0 flag from 0 to a 1. Right? This 0 flag was set with that compare operator that we did just before. Going to go OK. And now I'm going to run. And now it actually prints the real secret. It's a little buggy because you can't expect programs to run perfectly if you've just been screwing with the machine code. But you can see that it does print that. Right? And it just says Melvin is a virus. Kidding, no, he's a very silly bacterium. Melvin, remember, is the malicious Melvin program you saw in the PowerPoint before. Right? So just to understand the gravity of what we've just done, right? We have looked at the machine code of a program and changed it. We've also looked at the assembly code, the flow of program, how it goes from one block of assembly to another. And we've altered the flags register, right? That's those little gates based on those transistors we learned about on day 1. We have stuck a little electrical signal onto that reset gate that changed that one SR latch that then changed the flag for is it 0? And then when we read that flag later on in that statement, it is going to jump, it is going to change our IP to a different location because we changed that flag that was changed essentially in the state of those transistors, right? So going right down to the low level of it, we are able to change the execution of a program. That's very difficult stuff to do, right? It is extremely difficult to alter a program running, and that's why I basically made this one specifically to make it possible to do in the matter of 20 minutes. In most cases, it takes very smart people hours upon days to do that. And to do anything substantial, like making a Trojan horse that could, say, install a keylogger and send that data back to a server, if we want to alter Microsoft Word to do that, it would take you years, right? It's difficult to do, but it is possible. This is the groundwork of how it is doable. Any questions? right? Any comments? What do you think of what we just did, Judith? So the practical application of what we just did is, as I mentioned, we can create Trojan horses that way. That is bad, yes. There is a reason I'm teaching you how to do bad stuff. The reason for that is not that I want you to do bad stuff, right? In fact, I made you specifically say that you wouldn't. The reason for that is you can't thwart the bad guys without knowing how they work. You can't program a program to make it impossible to do this without knowing how to do this, right? So, know thine enemy kind of thing. So what the bad guys can do with this, they can create Trojan horses, they can create rootkits. If we do this with an operating system file, we can make the operating system do something it's not supposed to, and since the operating system does have root privileges, that means that we can get root access to a computer by disassembling the operating system files, right? And the last thing we can do is bypass passwords and license checks and whatnot in pieces of software. So if you're writing a piece of software that you want people to pay for, if you make it this easy to get past the license check, people are going to, right? So we'll take a look at a couple ways to prevent that from happening. The most important way is make it not a simple comparison, right? Make it not a hard-coded password. You know, the password was hard-coded into that application. You could have searched for the password, a rather unsecure password, found it right in the binary file, right? That is something that you don't want to do because someone will do it. What is better to do is encrypt it, right? You encrypt the password, and then the user enters the password, you encrypt that, compare it to the encrypted password, and that'll try it. An even better way is send the password to the server, and the server will check, is this legitimate? If it is, it'll send it back, and then it'll run the program. And in fact, an even better way is it'll send back a bit of machine code or a bit of other code that you can use that without that specific information, the program cannot run, right? So there are always people finding better and better ways to reverse engineer programs. You just have to make it so hard for them to do it that it's not worth it. They may as well just pay the price to buy your program. That kind of makes sense? Okay, so that pretty much wraps up our reverse engineering section. Unless you guys have any questions on that? No. So what we'll do now is we'll go back and set up an SSH server. So we will want to get into our groups for this.